Good afternoon, everyone, and welcome to this session on multi-scale QMM simulations. I am Davide Mandelli from INM 9 at FZJ, and I am one of the speakers together with Mirko Paulikat for these introductions to the tutorial. So before starting, I wanted to remind you that the tutorial will take place on the Yusuf cluster of the Jülich Supercomputing Center. And in order to access the computational resources that we allocated for this tutorial, you should get your credentials. And this is done on the Judor portal. And you should have received an email this morning. Otherwise, you can retrieve the instructions from the agenda clicking on this link. The procedure should take around 10-15 minutes. You could start now or wait until the end of the presentation, and we will wait at the beginning of the tutorial before starting to make sure that everybody have access. Okay, so we wanted to leave the vast majority of the time for this session for the tutorial, so the introduction presentation will be short. I will start by giving a brief overview of the theory behind the QMM molecular dynamics simulations. After that, Mirko will talk about some nice applications that he's working on. And finally, Bharat will give an overview of what you're going to do in practice in the next 4 hours. Okay, so as all of you probably know, all the brain function and dysfunction can in principle be traced back to the thousands of chemical reactions that occur during synaptic transmission. These include, for example, enzymatic reactions, transport of through transport membrane proteins, and the interaction between small molecules like neurotransmitters with neuroreceptors, which are again membrane proteins. Molecular dynamic simulations and atomistic molecular dynamic simulation are actually a very powerful tool that allow to study these phenomena. In fact, they allow to follow in real time and with atomic resolution the processes that occur during these processes. The goal of atomistic molecular dynamic simulation, in principle, are to get a complete thermodynamic and kinetic description of these processes, and this is important not only to get fundamental insight of these phenomena, but can have also a practical impact. In fact, they can be used, for example, to design novel drugs. One can identify 3 main challenges for performing atomistic molecular dynamic simulations of biological systems. One has to do with the theory, that is, one needs to come up with a model that describes accurately the interaction between all the degrees of freedom. The second one has to do with the size of the system. Again, in order to obtain results that are comparable with the one in experiments, the simulation box, one cannot limit himself to simulate a bunch of atoms. The models must be as close as possible to the real system, and this means that one needs to take into account the whole environment, which includes the solvent, the membrane, ions, and so on and so forth. And these generally can lead to simulations containing several 100,000 of atoms, which are very expensive. And finally, the last challenge is the one of timescales. That is, one needs to be able to simulate long enough trajectories in order to compute thermodynamic averages with adequate statistical accuracy. And when choosing the MD approach, it comes out to a trade-off between these three challenges. And here in this chart, along this axis, I'm plotting the accuracies of different models, starting from less accurate theoretical models for the interaction that are based on classical force field, going up to very accurate quantum chemistry approaches. And as you can see, as the accuracy of the methods increases, the time scales and size that one can simulate shrinks, as the computational cost of more accurate increases with the accuracy of the model. And in this chart, multi-scale QMM MD simulations stand out, as they allow to simulate with quantum accuracy very large systems. So they allow to study biological processes, and also for a relatively long amount of time. And at the moment, multi-scale QMM simulation represents the state of the art of for biochemical simulations. So what is now the idea behind this approach? It is actually quite simple. For example, one can take one can think of an enzymatic reaction one is interested in studying, and in the enzyme, the actual reaction involves few residues, while the vast majority of the system in the vast majority of the system is not really important to describe explicitly the electronic degrees of freedom. So in QMM interaction, one divides the simulation box into two parts: the quantum mechanical subsystem that includes all the atoms of the system where the physics we are interested in describing at the QM accuracy are present. And here I indicate with this quantum mechanical Hamiltonian the fact that the interaction here are described at quantum mechanical level, and the rest of the system, which is called the usually referred as to as the molecular mechanics subsystem, which contains the vast majority of the degrees of freedom, and that is treated using cheaper parameterized potential, as described, as indicated here by this molecular mechanics Hamiltonian. Of course, the two systems cannot be treated as independent. One is to take into account the effects, the mutual effect of the MM part on the QMM part, and vice versa, and this is taken into account by computing mixed interactions between the QM and MM regions. In QMMM simulation, the usual approach is to adopt different softwares to compute the quantum mechanical interaction and the MM interactions, and to couple them through an interface that takes into account for the mutual QMM interactions. And in the tutorial of today, we will use the MIMIC QMM interface that has been designed as an interface between the density functional theory code CPMD for the QM layer and the GROMACS code for the classical part of the system. MIMIC has been designed to be very efficient, and it actually allows to run in parallel the quantum mechanical and classical simulation layer to achieve to achieve speed up. Okay, in this slide, I will just go through the basic steps of a QMMM molecular dynamics simulation for those who are new to this. So the MIMIC-based QMMM simulations, we adopt the so-called Born-Oppenheimer approximation, where the dynamics of the electrons in the quantum mechanical regions are assumed to be decoupled from the one of the nuclei. With this assumption, we can consider the electrons to be always in their ground state configuration for the given positions of the nuclei. A Born-Oppenheimer molecular dynamic steps, therefore, involve first solving the quantum mechanical problem for the QM subsystem, so solving the Schrödinger equation, given the quantum mechanical Hamiltonian, describing the interaction within the QM system, and the QMMM interaction potential. The result of this equation is the ground state wave function describing the electrons, and the function here, E of R, which is the ground state energy of the system, that is a function of ionic position. Given the ground state energy and the potential, interaction potential in the classical system, one can compute the forces acting on all the ions by taking the negative gradients of this quantity. And once the forces are computed, one can update both the position and the velocities of all the degrees of freedom in the system by solving a discretized version of Newton's equation. Given the new position of the ions, then one iterate these two steps for a user-defined number of steps. The result of this process is a sequence of snapshots or configuration of the system as a function of time that can be used then to compute time averages of any observable one is interested in. Now, the one drawback of this Born-Oppenheimer approach is that at each time step, given the nuclei position, one has to solve the Schrödinger equation. And for a large system, this can be quite expensive. An alternative approach to Born-Oppenheimer molecular dynamics is the so-called Karp-Marinello molecular dynamics. That is the one that you will be using in the tutorial. I will not go into the details, but with this approach, basically, the Schrödinger equation is solved once and for all at the beginning of the simulation. And then one propagates in time a fictitious dynamic of also of the electrons, meaning of the ground state wave function. And this allows one to avoid having to solve the electronic problem at each time step. And under some assumptions that can be checked at runtime, it can be shown that the trajectory obtained in Karp-Marinello molecular dynamics is the same as that of a Born-Oppenheimer MD. And therefore, one can use this approach to obtain similar results, but at a much with a great gain in terms of speed up. We have prepared a tutorial to run Karp-Marinello molecular dynamics, but if you are interested in actually comparing the performance between these two methods, you can ask us and we will guide you through how to set up the input in order to check these two approaches. And as a last slide, I just want to mention that the MIMIC framework, we are close to the first official release of the MIMIC code. So those who are interested can keep an eye on the official website. And with this, I finished my presentation, and I will leave the stage now to Mirko, who will show you some applications he's working on. Please, Mirko.
Hello, everyone. Can you hear me?
Yes.
Great. So then I share my screen. So, okay. I want to show you a specific application where we study the ligand protein complexes. Yeah, I think it's quite clear that such ligand and protein so we are very important also from a biomedical point of view, as such ligands can act as inhibitors, and I am currently studying a specific system which is a so-called P38 alpha mitogen activated protein kinase. It's a soluble protein, but it's also present in neurobiology, and it's engaged in a multitude of stimuli, such as inflammatory cytokines, and due to UV irradiation and so on. And it regulates various cell functions and is also related to a lot of diseases. So it's a nice target to develop drugs and inhibitors to modulate the activity of such kinases. The structure is shown here. It's a PDB structure with a ligand inside. It's from it has here two domains or two parts: the N lobe and the C lobe, and the active site is directly in between. So the N lobe and the C lobe are connected via a hinge, and here's an ATP binding site, and here's actually the active site, and it's a very dynamic system. So the activity of the kinase just accesses if here the site is dual phosphorylated, and we get dynamic changes so that the substrates can bind and that the full activity is reached. Yeah, so it's a nice target or an interesting target, and we want to study with these QMMM methods the atomistic description on how is the binding site, or how changes the binding site, or what are the interactions between the ligand and the protein. For the specific system, there are always different effects which stabilizes the ligand, and I'm studying currently it's the so-called ligand 2G, which was proposed in 2011 as a potential inhibitor. And yeah, there are several interactions which are present, hydrophobic interactions from alanine or valine residues, also from threonine residues, which stabilizes the ligand binding inside the binding pocket, but also polar interactions, hydrogen bonding here with the backbone of a methionine residues, which forms hydrogen bond and stabilizes. But there's also this binding pocket is also solvent accessible, partially solvent accessible, so that water molecules also interact and stabilizes or determines the binding affinity of these inhibitor. And yeah, to appropriately describe these protein ligand binding and the ligand binding mode, we use molecular dynamics. As I mentioned before, that's a very dynamic system, and also to include an appropriate description of the ligand, and in some stages then also in the environment we use QR methods to describe the ligand, and their interactions with the surroundings. Now the protocol we are using, so that's a bit the technical part from how we implement the approach or execute the approach Davide has presented or introduced with QMMMD. So it's always the starting point is that we have done a classical molecular dynamics of this system to get a starting structure. a reasonable starting structure, which is well equilibrated, and then we have to make some decisions, technical decisions for the QMMM simulations. That's, for example, the QM region. In the moment, I'm just specify the ligand atoms in the QM region, and then there are also the DFT methodology, which functional we're using. Here we use the blip functional, and also the plane wave cutoffs. You get much more details in the tutorial today. And in my simulations, I use Born-Oppenheimer dynamics, which with typical time steps of 0.5 femtoseconds. And one should also check the scalability and performance for these simulations. So on how many cores we can run these simulations efficiently in parallel. And I've shown you such a scalability plot here, the speed up with the number of nodes, and up to roughly 392 cores for this small system. We get an efficient speed up of roughly 70%. So that's these are the settings I'm now using to simulate such a system, and with that we can obtain 28 picoseconds per day on 8 nodes, which is really good for QMMM simulations. And starting from the MD simulations, we have to run a re-equilibration protocol. So because we're changing the potential which we are using from classical molecular mechanics force fields to QMMM potentials, so we need to relax the structure in an annealing procedure or an optimization procedure, and then reheat the system and equilibrate it again on the QMMM level, and then finally run our production run to analyze the structural and energetics of the system. And in fact, this protocol you will go through the tutorial today as well. And then some analysis of the systems I'm studying. I've looked at the, as I mentioned before, on the binding pocket, which are the structural determinants which stabilizes the ligand inside the binding pocket. And of course, we are looking for structural determinants which change between the MM description and the more accurate QMMM description. And here's a small example. It's the hydrogen bond interactions with the pyridone moiety. So here this oxygen atom, when we analyze the classical MD simulations, we found that preferably a water molecule is hydrogen bonded, and a close lying lysine residue points more array into the solution. And so that we have here preferred binding by water molecules. And if we run QMMMD simulations, these situations changes. Now I have to switch my this one. So I made a small movie. So we started from here, from our MD simulation, from our classical MM structure. And if we run the QMMM simulations, what you observe is that now preferably such a lysine residue starts to interact with the ligand, which is then also stable for the remaining part of roughly 50 picoseconds I've simulated up. So it's important to know the dominant binding modes of the protein residues with the ligand, to understand these binding modes and to optimize the drug molecules. Now sharing, going back again. Sorry. And yeah, to understand, seeing that here the interactions or seems to be more dominant or more stronger with the lysine residue, one can also make an electronic structure analysis on the ligand bound to the protein, and to estimate effects like polarization and charge transfer, which are actually not available in classical MD simulations, but can be analyzed with QMMR methods. And what we can, for example, do is to estimate the effect of the protein binding. So going from the in vitro structure to the protein bound structure, where we just remove here the protein environment, which are described by by molecular mechanics or force field charges, and have a look on the effect of what's happening when we insert it again into the protein. And what we can then, for example, plot is the difference density between both states, which gives us an estimate on how strongly polarizes the ligand, the protein environment, the ligand. And I've shown it here, for example, as we can see here, that's the ligand. And there are some stronger effects or some strong effects on the polarization or charge deformation from the lysine residue, which is interacting here with the oxygen. And we see that it seems to be strongly interacting with this one, probably because of the positive charge, stronger than just the water molecule. Yeah. And we can also estimate the overall effect of polarization. So how is the charges redistributed when we bring these ligands into the proteins? And it seems a rather small effect, but that's already significant that such different binding modes can be observed between the two methods. And with that, I finished, and I suppose that Bharat is continuing with the introduction to the tutorial.
Yes, thank you, Marco.
I have to stop sharing.
I hope you can see the screen now.
Yes.
Good. Okay. Hello, everyone. Having listened to what Mimic is and how Mimic actually works from Davide and Marco, now let's go on and actually do a practical Mimic simulation. So in this workshop, we will do a simple toy Mimic simulation that will help us to see how the software actually works. So before going on, I would like to remind you guys that you need to have access to the resources to actually run the Mimic simulations. So we gave instructions on, I think there's a document on the eBrains drive with detailing the instructions. The link to this drive was put on the website and on the emails. So if you have any issues, please put a link, ask a question on the chat. We'll be happy to help. I'll just quickly go through the steps that you need. So the first step is to register your account with UDOR so that you have access to the ULE supercomputing systems. Then you would have to join the project that has been assigned for this workshop, the ICE project, to get access to computer time. And then you can go on generating and uploading SSH keys to UDOR, the details of which are in the document. And then once you have the SSH keys, you should be able to remotely access USIF through SSH. Once you have accessed USIF through SSH, don't forget to actually copy the directory. Yes, so don't forget to copy the tutorial directory that we have provided in the Scratch folder. This folder contains all the instructions and data required to actually carry out this tutorial of the workshop. Now going to that folder, the main file that you need to look into is the PDF, the tutorial PDF, which contains all the instructions necessary to actually carry out the tutorial. This tutorial, I believe, is also posted on the eBrains drive. So you can have a look at it there if it's easier for you to read it from there. The tutorial directory contains a list of 10 folders corresponding to each step that you need to perform for the simulation. So the details of each step are provided in the manual, and all the required data to run the simulations are provided in each of these folders. So if you take a look at one of these folders, let's take an example of step 6 annealing. So this contains a file step6.sh, which is a batch script. And if you run the batch script, you will have, it will generate all the required data for you to run the simulation. So it will output the CPMD input files and all the other files that you need to run an annealing mimic run. We are in the usage system, we are going to use the Slurm batch, Slurm job scheduling system. So you would need to create a Slurm script to actually run the job. The step6.sh conveniently generates the script for you. So all you need to do is run sbatch on that script. But we would still recommend you to read each of these batch scripts in each of the steps to actually understand what it's doing and how you would actually run a mimic run once you start on your own. Also, details on these batch scripts and everything is given in the tutorial manual in the PDF that I linked earlier. The folder also contains a reference folder containing all the list of ideal outputs that you should obtain after running the simulations. So go ahead and run the simulation for each step, and then check your output with the output that we have posted. And if there are any issues, again, you can come back to us. Now, coming to the goal of this tutorial, the goal is the main aim is to run a QMM simulation of acetone in water and calculate the dipole moment. We would then compare this with the dipole moment of acetone in a vacuum, calculated at a pure QM level, to get an idea of how the changes that happens when you solvate a system and how QMM can improve your calculations. So we have 10 steps for this. The step 1 is just to prepare the inputs and the topologies for the rest of the steps. And step 2 is just a quick pure QM simulation of a pure QM simulation of acetone in water in acetone in vacuum. You would do this in CPMD. And then we would take this acetone, solvate it in water, and carry out an MM equilibration step. Having obtained these structures at the MM equilibrated step, we would then carry out mimic QMM simulations, and then finally calculate the dipole moment of acetone in water. Now, I think, as Mirko mentioned earlier, to actually run a mimic simulation, mimic QMM simulation, you would need to do a preliminary MD step. So you would need to do a calculation at the classical molecular level before you could actually start QMM. So for this, what you would need to do in the beginning is, again, like I mentioned, create the structure files, generate the structure files and the topology files. This is done in step 1 of the tutorial. Then you would need to carry out the solvation, minimization, and classical equilibration at the molecular dynamics level. This is done in step 3 and 4 of the tutorial. Once you have done these steps, you can confirm that the system is equilibrated and that the energy is sufficiently stable, the RMSD is sufficiently stable. And once you have that structure, we can transfer that on to start a mimic simulation. So to run mimic QMM, you need to run GROMACS and CPMD in parallel, that like Davide had mentioned. So for that, you would need to have separate GROMACS and CPMD input files with special keywords in each of them indicating that this is going to be a mimic run. So these input files can be easily generated through the mimicpy code that is provided as part of the mimic package. All you need to do is you need to take the outputs of the previous step, that is the GROMACS topology and the equilibrated coordinates, pass it through mimicpy, and you would obtain the GROMACS TPR and the CPMD input required for mimic runs. So this is done as part of step 5 in the tutorial. Now, once you actually have these, you have the mimic inputs, what you need to, now we can actually start the mimic QMM simulations. So as a first step, you would have to perform annealing. So annealing is you would slowly remove the kinetic energy of the system and reduce it to 0 Kelvin, almost 0 Kelvin. So this is done as part of step 6 and 7 of the tutorial. You would take the structure and reheat it back to 300 Kelvin as part of step 8 in the tutorial. This is hoped to, what this is meant to achieve is to equilibrate the system at the QMM level at 300 Kelvin. Once you have an equilibrated structure at the QMMM level, we can then start with the production runs. We would then do QMMM dynamics as part of step 9, and finally calculate the dipole moment of acetone and water as part of step 10. Okay, so that's it for now. So I saw some thumbs ups. I'll just show you how step 1 and step 2 work, just to keep everyone on the same track. So again, so step 1, when you execute the command, it would run GROMACS and generate the topology and the coordinate files that we require. So this is pretty standard. I think there should not be any issues in this step. And then you can go on to the second step, which is the CPMD script. And this script actually would be your first CPMD run. So a pure CPMD run with no mimic. If you take a look at the script, it would actually output the CPMD input script that you require and the Slurm input script. So if we go ahead and run it, step a.sh, sorry, yes, you would see a CPMD input script and a Slurm input script. So this CPMD run would run a pure geometry optimization at QM level for CPMD. Yes.
Bharat, yes, I think that Bharat, yes, has a still problem with the step 1, from what I understood. Maybe you can show also that.
Okay, thank you.
And try to clarify like the module load, because I think that she's trying to run the commands from the bash, like the GROMACS command from the terminal, and I think that she's missing the executable.
Okay.
Okay, I think that she got it. Yeah.
Okay. There might be issues with the executables on the Jupyter lab. So if there are issues, it might be better to just SSH on a normal terminal. But if not, you can continue with Jupyter.
Okay, I think that now everybody should have done step 1.
Okay.
And please, we suggest that you open with the VI or other text editor these bash scripts. There are comments inside so that you can see what's actually going on.
Yes, and if you have any questions, just post it on the chat. So,
and also we are few. We are just 3 people, so you can also just switch on the mic and camera, and then we'll chat as you prefer.
Yes. So I will repeat this again if you need to, but just to give an introduction to step 2, what I have done is again execute the script, the bash script provided for step 2. Step 2 is split into 2 parts, 2A and 2B. So for now, you would execute the bash script for step 2A. It would give you a CPMD input and a Slurm input. This is just a pure geometry optimization of acetone. So once you have the Slurm input, you would run sbatch slurm and pass the slurm script. So this would start your CPMD run. So once everyone has started the CPMD run, we can go on to the next step. So once you have this run running in the background, just post a thumbs up or something like that. At least what you should be getting if you run if you run the simulation, if you're able to run the simulation, and you take a look at the reference folder, you would see the following files. So the details of most of these files are again given in the tutorial document. But what you would get, the most important file to look at is this output file. So this opgeo-out, and that would. This file empty?
Yes, because it's in optgeo.out. This is the output of Slurm, and in the for pure CPMD it's empty.
Okay, so I'm sorry. So this file opgeo.out is the output file of CPMD. And yes, so this is the output that you would expect. So I can go through this in a slightly in a bit of detail. So you would have this CPMD header in the beginning, and what you would need to check, it would print out the details of the input that you have specified. So the atoms in the system, the pseudopotentials that you are using. This is again just a restatement of what you have given in the input. Some technical details on the number of CPUs and how it's the number of mesh sizes and stuff like that. And then it would actually start with the geometry optimization. And you can see how well it's going in these few steps, in these what it's printing over here.
I think that Rupa at least got it running, so she should be able to follow the simulation. Yes.
Let me see if I have it running. Yes. So since it's running, like I think Andrea has already, I think David has already written it out. But the easiest way to monitor the simulation is to do tail F, the output file. So you would see it outputting each new geometry optimization step in real time. And now it's just ended. Like we said, it takes only a few seconds to run. So
maybe you can explain, I mean, what is a geometry optimization? What is what is happening? Yeah.
So what actually happens is, if you go through the output, what we have attempted to do is we have specified a certain input coordinate set of coordinates for the acetone, right? So this is not the most optimum, let's say optimum sort of configuration of the atoms at the QM level. So our goal here in step 2 is to actually calculate the dipole moment of acetone in vacuum, but we cannot do that before we actually optimize the structure itself. So what we do here in this step in 2A is to actually just optimize the structure at the QM level. I think I can open up the input, the input file. And so this are the set of keywords that actually tell CPMD to just optimize the geometry. So you can see here geometry optimize, and we give it certain convergence conditions. So basically we run the simulation until the change in geometry is around less than 7 to 10 power minus 4 at atomic units. So at the end of the simulation, we would obtain a structure which is given in this geop.xyz. We would obtain a structure which is optimized at the DFT level. And we would use this structure to calculate the dipole moment in step 2B.
Yes, there is a question. So Rupa is asking, how do you monitor how the optimization is going? So in the output, what you should look to see whether it is proceeding or not. Maybe you can open the output and see, compare 2 steps, what they should look at.
Let me go from the back to see something. It's easier.
Maybe you can describe briefly, very briefly, what are these numbers basically?
Yes. So let me see. I should start from the beginning.
I think that any step would do good.
Yeah, it's easier for me. Okay. So you have a list of, so what it does is that you would have to look for a block like this, where it says the step number, and it gives you a bunch of numbers where how well it's being optimized. So what you need to look into is actually it gives you the coordinates and the gradients, the forces at each sort of atom. And then what you need to look at is so you need to make sure that this number is going as small as possible.
Okay, but there are two things. Okay, so this sequence from 1 to 23 steps, this is the self-consistent step. So this is where when CPND is solving Schrodinger's equation for the given
Yes.
coordinates.
Yes.
Then there will be a step,
Yes.
and at the end,
Listing of the
given the force, there will be a step of optimization, and you will
Exactly.
get the new coordinates and the new forces acting on each atom.
Exactly.
And the geometry optimization ends basically when the forces acting on each atom is 0, ideally. Then, of course, it will not reach 0, but it will reach a threshold value that is set in
That
the
is set, yes, yes. That we set in the input file, which I think was around some 10 power minus 4 or something.
And after the atom coordinates gradients listing, there are some these DE thought TCPU. There are some statistics at the end of each step that you can look to have at a glance how the geometry optimization is proceeding.
Yes. You mean this one, right?
Yeah.
Yes.
And you can, I think that at the end of the output, there should be some like a summary of end of geometry optimization, and you see that you see the electronic gradient and nuclear gradient, those are gone below the threshold in principle.
Yes.
And all these, what we've discussed so far, you can find it even in more details in the supplementary information of the tutorial that Bharat prepared. So, Tabata, did you manage to run the simulation? Or is still? Okay. So I think that everybody went through step 2A. So now, basically, as Bharat was saying, we have optimized the structure of the acetone molecule in vacuum, and we can calculate its dipole moment. And this is done by running the step 2BSH. So maybe, Bharat, you can go ahead.
Yes.
Again, you can look at the inside at this script, but what it does is simply prepares a new CPMD input.
This one.
That instead of doing a geometry optimization, it simply reads the optimized structure and computes the dipole moment.
Here. So this is the new section that's added.
And again, to run to submit the job, you can just use SBatch and the new Slurm script that is also being generated. And this one, once it runs, it's a matter of a fraction of a second, maybe.
Yeah, I would just want to show you what we discussed now, the geometry optimization from CPMD, and also to visualize the different steps. We can use programs like PyMol or VMD, which are, I'm not whether sure if they are directly available on Yusuf, but that you get an idea what's happening at the different steps. I will briefly show you. The geometry optimization, you have, if you go into your, oh, I have to share my screen. If you download the file or the files or something like that, and then in the CPMD folder or in the second step folder, you see something an output file that means geo_opt. There are all the different structures from each geometry optimization step, which you can load, for example, with PyMol. Now it looks a bit weird because PyMol didn't recognize some of the atoms or connectivities. You just show the whole structure as sticks or ball and sticks models. So sticks and spheres. And okay, that's acetone, that's what you would expect. And here 3 carbons, the oxygen atom. And here on the bottom, there are also the number of different states. So state 1, that would be the starting point. And we needed 28 optimization steps to relax the structure. And you also see it's a bit bent. That's unlikely for acetone. And but if you play it now, you see how it relaxes into the preferred structure and also extends so that it's planar, for example, what you would expect from basic chemistry.
Okay, thanks, Mirko. Okay, if the simulation of the calculation of the dipole has finished, maybe you can show the output bar. So that would be the fourth step of the tutorial done. We have the dipole moment at the QM level of acetone in vacuum. So in this case, EPND doesn't have to do anything. It will just load the structure, the wave function of the latest step of the geometry optimization and use it to compute the dipole moment. And the dipole moment is reported at the end of the file here. Yes. Right? Okay, so this is, it's above, right? Here, property calculations. And this basically is reported in 2 units. You can copy, so you have the X, Y, and Z component of the dipole and its norm. So you can save these numbers and you will have to compare these numbers to the ones that you will get at the end of the tutorial. Did you all get the dipole from step 2B? Okay. So we can pass to step 3 now, where we will actually start preparing the structure of the system for the QMMM simulation. And I suggest that you read the introduction to the step 3 in the tutorial, where it is written in some more details why this is needed. So basically, the structure that we have prepared in step 1 use the structure of acetone in vacuum, and it just added in the simulation box water molecules in random positions. So this is a bad starting configuration because it can be a very high-end, corresponds to a very high-energy configuration of the system. If we would start the molecular dynamic simulation, classical or QMMM, from this structure, the simulation will probably explode. So it will be unstable. So the fourth step is to equilibrate the system, and this is done in 2 sub-steps. The first one is a geometry optimization at the classical level. After that, we will equilibrate the system at room temperature and constant pressure. And this will be step 4. And then we will proceed to set up the QMM simulation. So in step 3, okay, there is the usual automatic bash scripts. Again, we will copy the structure and topology files from the step 1 that are needed for GROMACS. Then there is an additional step where we define the GROMACS input, so the commands to set up the run in GROMACS. And if you look, there are comments. So we define what kind of run. We are using a steepest descent algorithm to optimize the geometry. And we set also here the thresholds to end the geometry optimization. And we set other parameters to define the model, how the interactions are computed. After that, we source the mimic.sh module that actually allows one to use the GROMACS executable. And then there is a GROMACS command that is used to create the TPR file. And the TPR file is the actual input file that is needed to run the geometry optimization with GROMACS. After that, so we create a usual Slurm script to submit the geometry optimization on Yusuf. So just running the script as it is. Again, here it is loading the modules and GROMACS. Then there are GROMACS outputs telling that everything went well. So we have generated the correct TPR file. And now we can just submit the Slurm mmgeopt script, and we can monitor the status of the job.
So you would use this file to actually monitor?
Yes, that's the output of GROMACS. So it seems the simulation is already running, and the simulation already finished. Yes. Okay, so it says steepest descents converge to
I can open
max force. Yes. So also here, basically, as in the previous geometry optimization, you will have several steps. Here, almost 3,000 steps were needed to converge. And at each step, what GROMACS output is the current, the energy, all the contribution to the total energy, and I guess somewhere also the force. Am I right? Or it so just okay? It just writes it at the end when it is converged.
You got cut off in between there, but I think you meant the forces, right? So the forces are printed here.
Yeah. So only at the end, right?
Yes.
Yeah. Okay.
Yes. And then the optimized geometry would be here, em.grow.
Okay. Again, let us know if you were able to run this simulation, and then we can proceed to the next step.
Okay.
Okay. I think that everybody got the output.
Okay. So you could visualize em.grow in a similar way that Mirko visualized the previous file to actually see what the optimized geometry would look like. In this case, there are also water molecules. That's the main difference because we solvated the system. Okay. Should I go on to step 4 then, Davide?
Yes. And we can proceed now to the next step, which will be the equilibration of the whole system always at the classical level. So again, you can move to the directory for equilibration, and you will find again the usual step for bash script. And also here we will have 2 of them. So we start from the 4a. This script again copies the structure and topology from the previous step. And it creates a new MDP input file for GROMACS that now, instead of doing a geometry optimization, it sets up a molecular dynamics simulation. And this molecular dynamics simulation will be at constant temperature. So you will have the setting of the thermostat that keeps the temperature at 300 Kelvin. You can show the reference T. Okay, and then there are other parameters of the thermostat, and the same for the pressure. So we want to do a constant pressure simulation at a pressure of 1 bar, which is approximately 1 atmosphere. And then there are other settings that you can read by yourself. They are commented on the right. Again, we have forced to prepare the TPR file starting from the MDP that is generated above, and this is done using the GROMACS gromp utility, and is done automatically for the script. And below, again, we prepare the bash, the Slurm script to actually submit the job. So you can go to this directory and run the step for a bash script. And again, here, these are all output comment on the from GROMACS, again, telling that everything went right. And we can submit then the equilibration step. This will take a few minutes to run. And again, we can, once it starts, we can monitor the output file of GROMACS, which is always called .log. Okay, now it's not running. And at the end of the simulation, we will need to check that the system is actually equilibrated. And we can do this by plotting several quantities, for example, the pressure, the temperature as a function of time, the total energy. And if everything goes well, those quantities at a certain point should start oscillating around the target value that we set in the input. Okay, now Yusuf is taking some time. So always let us know when your job is running, and then we can start analyzing the output. Okay. So I think that if you look at the PDF of the tutorial, there is the usual suggestion to how to monitor the simulation, which is the usual command tail -f, and then the file which is called, in this case, equilibrate.log. Okay, so Bharat's job is still waiting. Maybe Bharat, you can load the VMD module. Unfortunately, also VMD is not available for everyone here in Yusuf, but Bharat can show you the trajectory, at least, using the reference results.
I would have to X forward. So give me a second, I'll have to relog in.
Okay.
Yeah.
I think that I saw that the simulations of everybody are running. So you can look at the step 4b.sh script and at the relative part in the corresponding part in the tutorial to generate to monitor actually the simulation and check that it's actually equilibrating. Again, we already automatized everything. So just by running the step 4b.sh script, it will use gnuplot to produce a PDF file with the trajectory of the potential energy, kinetic energy, total energy, temperature, pressure, volume, and also density that you can either download locally or try to visualize from a remote using, for example, EVINS. So once you run this script, you can list, yes, and you should find an equilibration.pdf file. Okay.
Yes.
Mm-hmm. Check if it is not empty. Or okay, you are downloading it. Okay, go ahead.
I mean, so this is one of the cases where Jupyter Lab might be more helpful. So I would view it in Jupyter Lab without downloading it.
Okay.
So I can just share the screen. I'll just change my screen. So this is how it would look like.
So the simulation of Bharat was not finished yet. So the curves do not reach the end of the plot. But you can see that the potential energy, it started from somewhere around minus 24,500. That is the starting point. So our geometry optimized geometry from the previous step. And then as the system heats up, the potential energy also increases. And then it starts oscillating around its average value. And in the second page, we have the kinetic energy. The fluctuation of the kinetic energy are much larger. So here is not really easy to see, to check whether it has equilibrated or not. Maybe you can go below and check that the temperature eventually actually is oscillating around 300 Kelvin. The total energy.
The total energy and the temperature are basically fine.
Yes, that's and there should be other two plots below.
Okay. Yes.
Also the pressure. Okay, and then you have the volume and the density below, which gives basically the same information.
Yes.
But we checked that basically 400 picoseconds are enough to equilibrate this system. So you can wait until the simulation is finished. I think that by now it should have finished. Also the one of Bharat, you can check the log file. Yeah. Okay, so we can we can produce the final PDF plots. Okay, so now the simulation is finished. We can check the temperature below. Okay, total energy stable. The temperature, yes, is oscillating around 300 Kelvin. Okay, so now we have our system at equilibrated at room temperature. And this is actually a better configuration from which to start to set up the QMMM simulations. So maybe before the break, we can also do the next step, which is actually straightforward, which is about creating the input file for Mimic. So first, let's check. Let's ask if everybody was able to generate the PDF, and maybe have a look. Okay.
Yeah.
And were you able to visualize it? Okay. And everything, I guess, was fine. Since this. Okay, so we can go on and to step 5, and I think that here Bharat is the expert, since he's actually, he wrote the MimicPy tool.
So in step 5, we would actually go about preparing our Mimic inputs. So for this, we would use this MimicPy tool, specifically with the subcommand prep-qm, which would help us to actually generate the CPMD and GROMACS inputs individually, which we need to actually run the Mimic simulation. So what we need for this is we would need the previous topology. We would need to start from the previous equilibrated.
Maybe, yes, sorry. Before starting, you can briefly explain. It is explained in the tutorial, I think, but you can explain why, I mean, it's so useful. Because in general, setting up, preparing the input file for a QMM simulation is not straightforward, especially for complex systems. And also one is not that runs only one QMM simulation. One needs to tune several parameters, so needs to change several parameters and run different tests. And one should prepare different input files for every run. So having a tool that automatize this is really, really helpful. And this is why Bharat and Florian and other students here put some time and effort in preparing this MimicPy tool.
Yes. Okay, so I will just explain this line and then I will go to the results of what that looks like. So once then you would again you would give the topology and the coordinates that we got from and then these parameters I will explain a bit later. But what that would do is once you run that script, you will get a new CPMD script as follows. And what it does is it adds 2 new sections, a Mimic section and an atom section. So this atom section you would have seen in the previous input file, which is basically how CPMD accepts the atom coordinates. The new section is the Mimic section. So what this section, the most important parts of this section that is generated by MimicPy is this overlap section, which basically tells the mapping between between the CPMD atoms and the GROMACS atoms. So when you run MimicPy, I will show you what happens when you run the command. But when you run MimicPy, it asks you what atoms you want. What atoms you want to choose to be in the QM atom, in the QM region. So given once you give it those atoms, what it will do is it will organize those atoms and it will put them in this section here. So this section tells what the GROMACS IDs of those atoms are and what the CPMD atoms of those IDs are. So CPMD knows how to match each with the other. And what it does is it matches then with these CPMD IDs, it matches that with the coordinates that are passed, that are given here. So the first atom would be the first carbon of acetone. The second atom would be the second carbon of acetone, and so on. So basically what it does is, what MimicPy does is, it rearranges the GROMACS atoms, which is selected as QM, into the format that CPMD would like to receive it in. And then it does a couple of other small things. So another important thing for Mimic is you need to specify the paths parameter, which is the path to the GROMACS TPR file. That is basically the engine which is part of the QMMM run. So this path is very important. And before running any Mimic run, you should make sure that this path points directly to the GROMACS TPR file that is running. In the next step, when we run, I think step 6 after the break, we will make sure to change this path to the actual path of where we're running step 6 from. And then the next parameter is the box parameter, which is just the box size of the whole system, not just the QM region, but the whole QMMM system. So this can be obtained from the GROMACS, the GRO file. It is converted into atomic units. A couple of other small changes that you need to make sure of is in Mimic, we will be, although this is a QMMM run, we will instruct CPMD to specifically run an isolated system run. So basically the QM system is in a box which is not periodic. So for that, we would need to use this thing called Poisson solver command. There are more details about the physics of this in the supplementary info of the tutorial. But the parameters for running an isolated system in CPMD is Poisson solver command, and you need to give symmetry as 0. We need to also specify the size of the system, but in this case of only the QM region. This again is automatically generated by MimicPy, but you might have to change this a bit, because often we have to add padding we have to increase the QM box to more than the actual size of the actual size of the atoms, because we need a bit of extra space for the plane waves to actually exist. So you might have to fiddle with these numbers a bit until Mimic stops crashing or you get a proper run. So that's one thing. And then
regarding, sorry, Bharat, regarding this last comment regarding with the box, this is also a requirement of the Tuckerman Poisson solver that is used to solve Poisson equation to calculate the electrostatic interactions, and how to choose the simulation box when using this Poisson solver. It is explained on the CPMD manual. Of course, we are using CPMD that has its own set of instruction and guidelines. And so you can also, when setting up QMMM simulation with Mimic, you should always have the CPMD manual at hand, because there is where you look how to set up each section. Yeah, please go ahead. Yeah.
And then the last thing is you need to specify the charge of just the QM region. So you can approximate this as the charge of each of the atoms, the charge of each of the atoms in the QM region. So this is done automatically again by MimicPy. It just reads the GROMACS topology, picks up the charges, and then sums them together. Using the charges as the total charge of the QM region should be enough in most cases. Now, I think we can actually run this. So if we run step 5, it will actually output all of these files. And when you run the MimicPy command, it will ask you what atoms you would like to add into the QM region. So for that, so what we would like to do is, before that, I would like to show you what the previous. So if we have a look at the previous coordinates, the GROMACS file, we can see that there's an acetone with a lot of water, referred to as salt. So we would like to select this acetone as part of the QM region, and the rest of the waters would be part of the MM region. So how MimicPy allows you to do that is to actually select atoms in a similar way to how you would do it in a visualizing software like PyMol or VMD or Charm. So we can just do this by noting that the acetone residue name is ACT, which we defined in our topology, and we can just tell it to we can just tell MimicPy to select all the atoms with the residue name ACT. So if we go back and actually run step 5 to start up MimicPy, and what we can do is now it will ask you for the instructions of how to add atoms to the QM region. So we can say add, which says that now we want to add something. The rest name is ACT. And then if you just press enter, it will, sorry. Yes. So it will add all the atoms with the residue name ACT, which happens to be acetone, into our system. You can add, this is a very simple system, but if you want to add more, you can add more. If you want to delete something, you can just say delete is ACT. Now the QM region is empty. Now we can add back the ACT. And then finally, when you're happy with how the QM region looks like, you can just press Q, and it will print out some commands of what it actually outputted. So the first thing it does is that it takes all the atoms that you selected and arranges them into a GROMACS index file. This will be used later to actually generate the GROMACS TPR file, which is the actual run that we want. It will then say that it generated the CPMD input script, the one that we saw earlier with the mimic sections and the atom section. And then it prints a bunch of other commands. It also runs GROMACS GROMPP automatically using this index file and using the MDP script that was passed. And it will generate for you the GROMACS TPR file automatically. So we have this GROMACS TPR file and we have this annealing.inp. These are the only two files required to now run a mimic simulation.
Okay, and we will do it after the break. So see you in half an hour.
Just to get you up to speed as to what we have achieved till now is, so we created the GROMACS topologies and structures. We calculated the dipole moment of the pure acetone in CPMD. We then solvated that acetone, optimized it and equilibrated it at the molecular dynamics level, and we created mimic input files for us to perform QMMM mimic. Now we will start with the first step of a mimic QMMM, which is actually equilibrating the system at a QMMM level. For that, we would need to carry out an annealing and a heating step. So now at step 6, we will be doing annealing, and for that you can look at the step 6 folder with the bash script step6.sh, and I can explain this a bit to you guys, and then you can go forward and do it. I'll give you time to do it, but what we're essentially doing is we will copy over the two inputs that we created in step 5, annealing.inp and mimic.tpr. And then what we will do is we will make certain changes to the input file, to the annealing.inp, and then we will create the Slurm script that is required to actually run a mimic job. So if you remember what I mentioned earlier in the previous step, is that if you take a look at the input file that was generated, let me see. Just give me a second. Yes. Okay. Yes. So what we need to do here is we have a new mimic section in our input file, and we need to add the right path to the GROMACS executable. So we need to make sure that this path is right. We need to carry out annealing. There's some issue with my mouse. Yes. So to carry out annealing, we have this set of commands, CPMD commands, that will actually do the annealing procedure. And you can read about this more in detail in the in the supplementary info of the tutorials, but this factor of annealing ions is quite important. It's the percentage of kinetic energy that we remove at each step, so that we reduce the temperature to 0. So we need to specify this number, and we also need to specify the maximum number of steps that we will run it for. So these 3 parameters are the extra parameters that we will add in step 6, right before running the simulation. So if you go back to the script, you can see here is this line would actually add the path to the GROMAX TPR that we are going to generate, annealing.inp. This would add the value of 0.99 to the annealing factor. And for now, we set the max step to 1,500. So if you run step 6, you will see the resulting CPMD input file has the right path. That's the current path. And it has the annealing ions here, 0.99, and max step of 1,500. Feel free to change this value if you feel it's not enough, but we can go ahead and run this. And once it's running, I think it'll take some time to run. But what you should do is you should again do the tail -F, and monitor the temperature, the change in temperature of the system, and let it fall to around 0 Kelvin. So now I'll let you guys do this, and then we can get back in around, I think, 10 minutes. This should maybe take 10-15 minutes. So just post any questions you have, or post a thumbs up when you're done. Okay, so I was finally able to get the annealing running. And so this is what I was talking about. If you tail the output, again, I'll just show it to you. So you will see that the third column, which is the temperature, you will see it decreasing continuously, which is what we would expect from an annealing procedure, where you continuously decrease the takeaway kinetic energy from the system. And we will wait till this simulation reduces the temperature of the system to around 4 to 0 Kelvin. So once that is done, I think 1,500 steps is enough for that to happen. If it happens before that, you can stop the simulation by typing this command, touch exit. But make sure that the temperature has reduced sufficiently before you actually type that command. So I'll give my simulation a couple of minutes, and then I'll...
Yes, can you check, Bharat, the max step in this simulation, how much is it? Because I think it's 1,500.
Yes.
So, I mean, and I think that if you look at this, the script step, it's written more or less how long it will take, the simulation. The bash script, try to open it.
Oh yes, I told them about that.
Okay, yeah. No, since I'm back, yeah. Okay, okay.
I think for most people, the run started before me, but so they would have already finished it. But
yes, it's finishing.
Go to the chat. Yes, I just checked the chat. Yes. So there was this message. Rupa asked, what value should you check? So what I meant was the third. Sorry, it ended at the right time. What you should check while the simulation is running is the third column, this one. So this one is the temperature. It prints out the temperature of the system at that iteration. So in this simulation, after 1,500 steps, the temperature reduced to around 4 Kelvin, which is fine enough for us. Sometimes depending on the system, you might need to reduce it further to around maybe 2 or almost 0. But 4 is fine enough for an acetone system. So we can go ahead to the next step. Before that, Davide, do you want me to talk about the BO?
Do you want? Did you do the additional step, or you want to skip it?
The Born Oppenheimer, right?
Yes. Yeah, we can do it quickly because yes, it's very quick. So basically, I prepare an additional script that is in Scratch. Now Bharat can show you how to copy it.
Let me get the Scratch folder.
It's -p-scratch. I see.
I always make a mistake. So I'm going to copy it.
Okay. And
so,
it's not inside. It's just in Scratch, not inside the
yes.
So it's just a step. You can step.
So this is an extra step that you guys can do. So within the Scratch folder itself, there's this file called step6-bo. I think let's post this on the chat. So if you copy, sorry. Yes, I'll post this on the chat. So if you run this command, this will output a new a bash script, which Davide just prepared, showing you how Born Oppenheimer would work.
So far, yes, all the QMMM simulation that you've been running were based on the Carp-Marinello dynamics that I briefly mentioned in the presentation. And as I told you in the presentation, I told you that this CP dynamics is much faster than the Born-Oppenheimer one. And so I prepared a script to run a Born-Oppenheimer simulation to show you that that's actually the case. And so you can see the speed up when running using the CP dynamics. So if you run this script, you will see that a new directory appears, BO. You can change within this directory, and here you will find the usual inputs. This is the new CPMD input, where you will see that instead of molecular dynamics CP, that stands for Carp-Marinello, now it says molecular dynamics Born-Oppenheimer. And the other change is that one parameter that is needed for Carp-Marinello dynamics has been deleted. This you can see by comparing this input file with the previous one. The rest of the input, the CPMD input, is exactly the same. Apart, of course, the change also in the paths keyword. So you can, again, submit the job. And to compare the speed of this simulation with respect to the one that is based on CP dynamics, you can look at the energies file. The energies file is better. The last column of the energies file tells you the CPU time needed to perform one step of molecular dynamics. So you see that here is already running, and it takes 0.36 seconds. Of course, this is because this system is very simple and we are running using a lot of computational resources. So it is fast also, Born-Oppenheimer dynamics. But if you stop this, if you Control-C and you compare to the last column of this Carp-Marinello dynamics, you see that here the time, CPU time needed for one step is roughly 1/3. So it's still a significant speed up. You can imagine that if usually running big simulation, you need to run them for weeks even. So a factor of 3 is a lot. If you can reach a factor of 3, then of course the speed up depends also on the system and on the setup.
Let's give them a few minutes to do this also, so they can see the difference.
And also here, you see also here in the energies file, the third column is shows the temperature. And also here you see that it is decreasing as it should. And in 1,000 steps or so, it should reach also well below 10 Kelvin. But this it was just to show you the difference in performance between the Born-Oppenheimer and Kappa-Agnello dynamics. Did you manage to run this additional step? Okay.
Yeah.
So if you want, there's no need to let this simulation run till the end, because we already did it with the CP dynamics. So you can kill this run. So you can do this using you can use skew to check to get the ID of the run. And then you can use scancel followed by the ID to stop the job.
So this is a very bad way to stop a mimic simulation.
Yeah.
Because after you use scancel, it would not result in, it would not output the last frames properly. So you cannot restart from that file. So if you want to restart from a file, from a run, so what you should do is to stop a run where you can restart from, you should use the command that I talked about earlier, touch exit. So it's called soft exiting. So you would softly exit from that run, and you should hopefully be able to restart from that run.
Okay, so if everybody finished with the annealing, we can proceed with the next step. Is it okay for everyone to go to the next step? Okay. Okay, Bharat, maybe you can continue with the tutorial.
Sure. So in step 7, what we actually carry, so what we need to make sure now is that the structure that we obtained in annealing, the one that we brought down to almost 0 Kelvin, is stable enough. Because if it's an we need to make sure if it's an energy minimum or not. So what we do for that is we take the previous structure that we obtained from annealing, and we carry out a normal QMMM dynamics. No annealing, no heating, nothing. And we try to monitor the variation in temperature to see how stable the system is. If the temperature increases too fast, too fast, around maybe above 100 Kelvin, it means that the structure we have obtained is not a stable minimum, and we need to re-anneal the system. We need to reheat and re-anneal the system to bring it to a different point. So this is just a test to make sure that things don't fall apart later on. So what we're doing in this test is, as I said, just running a normal CP dynamics and measuring the temperature.
Yes, by normal, you mean constant energy?
Yes.
Constant energy, constant volume dynamics. Yeah. So the total energy of the system should be conserved. That is the other check that one should do.
Yes.
Yeah.
Yes. Yeah. So this script.
So basically, yes. Sorry, yes. I will just comment on the last thing that I was saying, that if you see at CPMD section that we are creating here, there are no keywords controlling the temperature. So no thermostat, nothing here. We are really solving Newton's equation of motion without thermostat or anything. And so the energy should be conserved.
Yes, hopefully. So what we do here in the script is, again, copy over the input files that we require. We copy over the previous annealing. We copy over the previous mimic TPR. And then we copy over this restart file. So this is the restart file that is outputted by the annealing simulation, the previous annealing procedure. And we use this restart file to literally restart from that coordinate, from those sets of velocities and coordinates. So you can see that when we edit the CPMD section, we ask CPMD to restart from coordinates, velocities, and wave functions, which means it will look for a restart file. And this restart file we obtained from this previous annealing procedure. And then it's we have a mimic run. We run a CP run, and like Davide mentioned, there are no annealing keywords. There are no thermostat keywords. So it's a pure NV, a constant energy system. And then again, we change the paths. We always have to change the path in the mimic section. Make sure that the path is right. And we again output the Slurm script at the end. So if we run this and start running,
Okay, so this will take a bit longer. I don't remember how much. Check that it should be maybe in the step 7.sh. Maybe it's written there.
I think it was 10,000 steps or something.
It's 10,000 steps, but in terms of time, yes, 10 minutes. But here it is
okay,
important to run the whole simulation because we need to ensure that the configuration that we have is a good one. So we need to check at least that in these 10,000 steps, nothing strange happens.
So you would tail, you would tail the energies to again measure the temperature. So just a clarification, I think last time I mentioned to tail the output file. Where the energy is here.
The temperature, yeah.
Sorry, the temperature is there. In the energies files, in the energy file also, you would have a similar column, similar value of the third column, printing of the temperature. The energy file is more convenient, honestly. So you can just tail that.
Here the temperature increased because it started from 4 Kelvin, but it should stabilize. It should not explode, keep increasing. If it stabilizes, then we are fine. And actually, we can have a look at it with the GNU plot. You can so you can load the GNU plot. We need to first load the GNU plot. So there is a script in the previous directory. You can just run the. No, yes, you can stay. Yes, or you can run it here.
Does
Okay.
this create a PDF or does it need export?
No. This just loads the right stage, the right modules to have GNU plot.
Okay.
That's it. By running this script, then you will be able to use GNU plot from command line. There is an error, I think. In the very first line, there is a dash missing between bin. Yes, so this is a. But I think instead of running it, you source it. It's the same. It doesn't. Yeah. Okay. And then you can go back to 7. And if you are in X window, you can do GNU plot.
I'm not. That's why I asked.
Okay.
So I have an issue with X forwarding. So that's why.
So maybe in Jupyter you can do it, right? You have also a window open in Jupyter. Yes. I'm sorry I cannot do it, but with the VPN here, it's nothing is working.
Okay, let me check. If it generates a PDF.
No PDF is created here, right?
No, you didn't add that script, right? I can use a similar script to this.
Yeah, if you want, you can copy this and modify. Just the second part is fine. The first one is not needed. Because this was for Gromax.
Yes. Actually, we could just quickly edit, make the script and then post it on the Scratch. So we can tell them to copy it from there. That might be better.
Okay, Bharat?
Yes.
Yes, you find the script is called plot-test.sh in Scratch. You can just do a no, but just do a star at the end. CP blah blah blah. Ah, okay, well, is that one? Yeah.
This one, right?
So also, if you want, you can copy this script. Yeah, and basically, what it will do, it will plot. It will create a PDF with the temperature of the system as a function of time. And the PDF file is called test.pdf.
Yeah. Yes. Okay. I can just switch my screen and show you.
Okay. So it's not finished yet, but you see that it increased almost linearly at the beginning, and then at around 2000 step, it started to slow down. So it's a good sign.
I can continue till
Yes,
down.
and then maybe you can, okay, if you open this plot test,
Yes.
if you see now, you see that now I'm plotting the third column.
Yes.
Try
Oh, you want
plotting the fifth column. That should be the conserved quantity. So this is the energy that should be conserved. And if you look at this is not the temperature, but it's the total energy. And if you look at the scale on the y-axis, you see that basically it is fluctuating, but it's basically constant. So it's the fourth digit that is changing.
So I think I can post, if people are a bit confused, I can post that in the chat. So Rupa says it's increasing. I guess she means the temperature, right?
Yes, that's fine. The point is that it should not explode. Yes. So maybe it should reach around 50, 60 Kelvin, but not above 100 Kelvin and keep increasing.
Yes. Yes.
So maybe you can. Okay, you can do the following, but you can copy that. You can plot inside the reference directory, so that we have the full plot.
Yes.
So you copy the plot script inside the ref and just run it there, changing the column to 2, so with that or 3, so that we are plotting the temperature, and we can show the result. Just to clarify, this is a constant energy simulation. The temperature is not supposed to stay constant, so it's fine if it is increasing. The point is that it should not explode.
Yes.
Okay, yes. So you see, also here it is increasing. It starts from 4 Kelvin, which is the starting point from the annealing. It jumps up to around 50 Kelvin and then slowly increases, and then afterward around 10,000, we checked it, it's reaching a plateau, and then it stays more or less constant. But this is fine. It would have been better if the temperature would have continued to increase. Yes, exactly.
So the point is, it should not be, the temperature should not always increase with this slope. That would be very bad. So this slope is fine, right, David?
Yeah.
Yeah. So
and then there is the other parameter. I don't know if you want to enter these details. You can find detail about the stability of a Karp-Marinello molecular dynamics in the supporting information. But another quantity that you can check in the energies file is the second column. And that also should not explode.
this one.
Yes, this should stay a small number. Here, probably it will reach at the bottom, maybe 0.001. Is the fictitious kinetic energy of the electrons. You can find more detail in the in the supplementary information.
From a practical standpoint of view, if you have this script, if you have copied the script over the plot test, all you need to do is change this number to 2 or 3 or 5 to measure those columns. So the third column would be the temperature. The second column would be the kinetic, the fictitious kinetic energy. And I think the fifth one was normal energy, total energy, right?
Mm-hmm.
Yes. So you can measure each of these and see the variation. The easiest, the most quickest to measure is the temperature, which is what we're doing right now.
And again, you can even look at just at the energies file, and like we were doing before, just monitoring and check that everything is fine. So if you do tail minus f of the energy, you check, you look at the second. You see that the second, the temperature is around 60. If you go to the bottom,
yes,
yeah, the most important thing is that the second column stays a small number.
Yeah.
And the third one doesn't explode. Yes.
This is again fictitious kinetic energy.
Temperature. And then the fifth column is the conserved, the classical total energy. And that should be conserved. So these are the three things that you can check. Okay, I think that everybody now finished the simulation. Is it so?
Okay.
Okay, so the test was passed. So it means that the configuration that we have generated through the annealing procedure is a good starting point for the next step, which is the heating. So now we have to equilibrate the system to room temperature, like we did at the classical level, but this time at the QMMM level. So yes, you can navigate inside the directory 8 heating, and you will find the usual bash script that Bharat is showing you. And again, what it does is, yes.
The restart file from the annealing this time. So we don't start from the testing. From the test, we start from the annealing, step 6. Again, the TPR, the CPMD input we copy over. We make changes to the annealing in CPMD input script to change it to heating. We can open up the CPMD input script and talk about that. But once we make the changes, again, importantly, change the path in the mimic input file. And then we output the Slurm script so that we can run the job.
So yes, maybe you can show the new input file. Yes. You can comment it.
So this time we want to heat the system. So it's not about cooling, it's not about annealing, it's about heating the system. And we have a couple of new parameters here. Again, talked about in detail in the PDF. But the most important is this, the Bredesen ions and the temperature ramp. So here we say basically, here we specify the temperature from which to start the ramping. So I think we would need to change this to 4, right?
But it's not a problem.
Not a problem. Okay. So generally what you would do is you would have to look at the last temperature from the annealing, which is around 4, and put that value over here. So 4 or 3, it's about the same value, it's fine. And we would like to ramp up the temperature to 340 Kelvin. So we would want to heat up the system to 340 Kelvin at a rate of 20 per time step. So this is quite a high rate. If depending on how the system behaves, if the system is a bit more unstable, a bit more finicky, you might have to reduce the rate of ramping. But for an acetone system, this is fine. So you have anything more to say, David?
No, it's okay.
Okay. So now once we have that script running, we can, as usual, run our batch script on Slurm, and we can see what it looks like. And in this case, if we start tailing, we would again monitor the temperature, but this time we would see it increase. So,
and always you can keep an eye also on the second column, checking
yes,
that that number doesn't get too high, which means that the Karp-Marinello dynamics is stable.
in a Born Oppenheimer, that's irrelevant. That,
The Born Oppenheimer, the second column will just print out zeros because that quantity is not there, it's not defined. And I think that we can let it run, let run also this simulation until the end.
Yes, yes.
Yeah.
So if the previous test had failed, this would probably blow up. This heating step.
If you can download maybe one trajectory to show at a certain point another movie of the actual system, it would be fine.
Okay.
Maybe just as heating
heating?
or yes, just check maybe the heating. Check the input file to see whether we are printing the trajectory. Because I didn't want to create too big files, so I might have put the keyword to a very small or large. So trajectory sample 0, so it's not printing the trajectory. Okay.
I mean, it might. So this is also something we can talk about. So if you want to visualize a mimic system, like how the mimic simulation is running, since mimic essentially consists of GROMACS and CPMD running in parallel, both of those will separately output their own coordinates. They should be the same, but generally what happens is the CPMD coordinates will be shifted by a certain value with respect to the GROMACS coordinates, but they're the same. So you can choose to visualize either one of them. In practice, personally, the mimic.trr file, which is the one outputted by GROMACS, is a lot easier because it's more supported by PyMol, VMD, etc. But you can also, the CPMD run would also output a file called trajectory, similar to this geometry or geometry.xyz. You could also visualize that. It might help in debugging. But in our case, we purposely set that to 0 so that it doesn't take up too much space.
I think that Mirko will soon show you a movie of the system that we have simulated.
Okay. I think he might visualize the TRR file. That's good. Also, the TRR is easier to analyze using MD analysis.
And of course, you can download locally the whole directory, and then you can use even when you have time any tool that you like to look at the trajectories.
So shall I briefly show the
Yes,
Yeah.
TR file? So property, okay.
go ahead.
So as mentioned before, I'm using PyMol locally on my laptop. So, but you can also download the trajectory and all files to your local machines and using your visualization program, which you usually are using to visualize trajectories, VMD or PyMol, or there are several others, I suppose. I've copied the GrowMax structure file. So you, for visualizing the trajectory, the GrowMax trajectory in PyMol, you have to load one structure file at first before you can load the actual trajectory. So here I loaded the system. Here on the top, you see the acetone molecule, and it's surrounded. It's, of course, you have to imagine that's a periodic system. So it's in this cubic water box, or yeah, it's cubic, right?
Yes, more or less.
More or less, okay. Yeah, and after that we can, or maybe a bit to visualize the acetone in a bit more detail. First select it and then show it also with spheres. And yeah, then we can load the trajectory, which we have generated with Mimic. We are now in the heating directory. Yeah, now it's here in the center, the acetone molecule, and if you just play, you'll see how the system evolves with the time.
Yes, it
Anything
is
to
really
add?
simple. It doesn't do much.
No.
I think this is fine. We can check if the simulations are finished.
Sure.
Yeah. I mean, but even if it's a simple system, as I mentioned in my talk, I've used exactly the procedure in much more complex systems.
Mhm.
So
Yeah, the tutorial goes through all the steps that are needed also for complex systems. Yes.
yeah,
Of course, these movies are not that exciting. That was my point.
yeah, exactly.
So do we let it run till 340 Kelvin?
I think that it's already stopped because I set the max step to 5,000,
okay.
which is around 300. Yeah.
Okay. Yeah. Okay.
Yeah.
I didn't know that.
So probably also everybody finished running the same
Yes.
simulation, dating. Yes.
If people are done, we can. Good.
Okay. So now we have a. If we want also here we could plot the temperature and check it and plot the energy, so you can reuse the plotting script, modifying it. But I think that we can move on to the next step. So we finally have our equilibrated acetone in water at the QMMM level, and now we are ready to start with the production run.
Yes.
So a production run is just a constant temperature simulation that we run long enough in order to compute thermodynamic averages.
I think I can generate the script so we can talk about it, right?
Yes.
So if you run step 9, you will get this production.inp.
Yes, and what changed? Yes, go ahead.
Yeah. So what changed was that we are again restarting from the previous file, this time from the heating. And what changed in this case is we have changed the thermostat. So we again want to run an NVT simulation, which is at constant temperature. But unlike the previous case, we are going to use a no-say hover thermostat. So that's why we use the no-say command. And this time it's not a ramping. We want to maintain the temperature at a constant value. So we just say 300. And then we run it for, I think, 10,000 steps. Yeah.
Comment also on the store and rest file for the computation of the dipole.
You want me to comment on? Hello?
Yes. Yeah, you can go ahead.
Okay. So the store. So this time we want to actually visualize the trajectory. So we're going to store the trajectory at every 10,000 frame, and we are going to create. So we created like how we created restart files in the previous annealing and heating steps. We're going to create another restart file, but this time at every 10th step. So you will see why in the next step, where we calculate dipole moments from these 10 restart files. But this command says that we're going to create 10 restart files.
Yes, 10 restart files every 10,000 step, which is the keyword before that.
Yes.
So
yes,
this is
every
at the end. Yes.
Step. I think I said every 10 step.
Yeah.
Yes. So 10 restart files at every 10,000 steps. So instead of having restart.1, we would have restart.1, 2, 3, 4, 5. And we will use that information to calculate the dipole moments in the last step.
So this is how we save 10 snapshots of the system during the simulation. And then we will use those 10 snapshots to compute the average dipole moment of acetone. Yeah.
So if we go ahead, do a normal procedure of running the simulation, of submitting the job. And as usual, we could tail the energies to monitor the output. And in this case, the temperature, the third column would be constant. I mean, hopefully it should be around 300 Kelvin. This will take some time. We just need to equilibrate the system for the 10,000 steps that we provide. So once it's done, you guys can put a message on the chat. Okay, looks like it's done. So if it's finished for the others, yes. Okay. I think so. It's finished for you also. So you can see that it with 10,000 steps and depositing restarts, 10 restart files, we can see the 10 restart files over here. So restart.1, and then restart.1 to restart.10. So these are the 10 restart files that we have. And we would use these as snapshots to calculate the dipole moment in the last step. So if we go to the last step, sorry, yes. So in the last step, we have again 2 sub-steps. If you take a look at step A.sh, we have the usual thing of copying the input files, the GROMACS, the CPM input files, and in this case, we copy all the restart files from the previous production step 1 to 10, and we add a new section here called called properties. It's not a new section. We actually used this section, the same section in step 2, where we calculated the dipole moments in vacuum. So we used the same sort of code, but this time calculated dipole moment in a QM-MM calculation. So if I run that step, if I run the script, it's taking a couple of minutes. Okay. We can see that it created 10 folders. So this is just for convenience. We have 10 folders, and each of those folders has one copy of the restart file and the same copy of the input file that we require. So we need to go to each of these folders and run the batch, the Slurm script in these individually. So you would have to run 10 steps in this case, and so on. It shouldn't take too long. Oh yeah, I forgot about this. So actually, Davide, we could just go ahead and uncomment this line, right?
Yeah.
Yeah. So the step A batch script would, like you saw, output 10 folders, each with its own copy of the restart file and the CPM input file. We could go to each of those files and run the sbatch command individually, or we could just uncomment this command, which would run it in a loop. This is probably a bit easier. Should have done this in the beginning. Sorry. Yes. So you can see that it's submitting all those jobs individually. So give it a couple of minutes to finish. And when you're finished, just again, post something on the chat. So I guess it finished for the others. It's still running for me. Let me just check. Okay. So if it's done, What we need to do now is we need to essentially go into, take a look at the output of each of the files and look at the dipole moment, the one that we talked about earlier. So the same section that we looked at step 2. So we need to take this dipole moment, read it for each of the files that we ran, and average it over. So we would have 10 dipole moments, which we then average over. You don't need to do this by hand because we've already prepared a batch script, which is step 10b, which essentially does this. So it loops over each of those the output files, grabs the dipole moment, and then prints out the average in a DAT file. So if your simulation is done, you can just execute step 10b, and you should have the dipole moment of acetone and water at the QMMM level. So I'm still waiting for my run, but if you're done, you can go ahead. I think we have the file. Yes. So just for reference, I mean the file is given in the ref folder, and the resulting dipole moment average would look something like this. So this is what the file would output, and you can compare this with the previous value that we obtained from acetone and vacuum. Okay, if you were able to calculate the dipole moment, that would mean that you're done with this whole tutorial. If you're not, you can go ahead and still continue. Maybe go through the previous steps, see if you miss something, you want to read a bit more. We have almost half an hour more. So it ends at 6:30 p.m. So we have some more time. But essentially we're done. And congrats, we've completed you've completed your first mimic simulation. So hopefully this made you excited a bit about running mimic simulations, QMMM. And we'll still be here for some time. So if you have any issues, any questions, or even about what we wrote in the supporting information of the tutorial, go ahead and then you can ask us. So just, I guess, to make it easier for people, uh, you can always, I think there was a question about downloading the whole thing. So the easiest way to download the whole tutorial is through Jupyter. I can show you how that would work. Let me share my screen. Give me a second. Yes. Okay. So assuming you're in your home folder, and this is of course the tutorial that you want to download, you just need to right click and there should be a download. Oh, yes. So what you would need to do is you would need to zip this file. I think there used to be an option to zip this file right here. but now I think they just updated it. So you would need to zip this file in the terminal, and then you should be able to right click it like any other file, and you should be able to say download. So for example, if I want to download just this PDF, all I need to do is right click and say copy down, just say download. We can actually prepare a zip file for them so that it's easy for them to download. I can actually do it. Davide?
Yes. So I will prepare the zip file of the, it will be of the tutorial without their results, but okay, they are in the reference. I don't think it's a problem. Okay, I will do it.
Okay. So Davide will prepare a zip of the results. I mean of the tutorial files. It'll be on Scratch, right? Davide?
Yes.
So you can copy it